Gonna wait for the confirmation that we exist. At this point, we should exist. Just wait. I just require somebody to confirm our existence in the chat, and then the second that happens, then we collapse the wave function, and we know that we exist. Because I could
Well,
see, I could see
that's the
people.
way to do it.
I believe
I
that's
exist in
yeah, yeah.
several places at once.
That we are uh, we're the Boltzmann brains that are observing. You guys who are watching this show right now, you are the Boltzmann brains that have suddenly appeared in the universe and are now observing us, confirming, I don't know, the Copernican principle or something. All right. Marty the Martian says that we exist, but they don't. So as long as one of us exists. Fred, it's good to talk to you again. Who are you? What do you do?
I'm very well, thank you, Fraser. And I'm absolutely delighted to be able to talk to you again as well, especially on an auspicious day when we've got the news of water on the moon and all the rest of it that's going on.
Oh,
Uh,
you.
Thank you for having me on the show.
I mentioned this before we started, but I won't go through my rant again. So, yeah, yeah, no, great, water on the moon, hooray! Um,
Yeah.
so, but yeah, who are you? For anyone who doesn't know, anyone who I guess lives on this hemisphere of the world, who are you?
My name is Fred Watson. I was for 20 years the astronomer in charge of the National Observatory, or the National Optical Observatory, which was at a place called Siding Spring
Oh,
Mountain in rural New South Wales, near Coonabarabran, a town that has got an astronomical ring to it because of the observatory there. In fact, it was what was called the Australian Astronomical Observatory that I was astronomer in charge of. That changed its governance a couple of years ago. And so my job changed as well. I didn't go, as most of my colleagues did, to the university sector. I stayed with the government sector because we were a nationally funded facility. And they found a job for me, which has the delightful title of the astronomer at large. So I'm Australia's astronomer at large, which means that I'm kind of everywhere. Is exactly as you said. I'm a wave function, really, not a
right,
person.
yeah. You're as big as you need to be, as big as Australia needs you to be. You're right there. So what does the astronomer at large do? I mean, like, what would your typical I don't know, month look like?
It's a lot of it is this kind of thing, Fraser. It's doing what you and I both love. I know you've got the same passion for getting the word out as I have, and so the role itself is an outreach and advocacy role. So it's a lot of it is talking to the media, talking to other scientists, because having been a working astronomer, I know a lot of people all around the world, many in your country, as well as here in Australia and in Europe. And so find out what they're doing, which is fabulous. It means I can go and talk to people and get all the latest exciting stuff, which they often have to say, you cannot possibly tell anybody about this because it's embargoed.
Oh no. Oh,
Yeah.
oh, man, you're triggering me.
I'm sorry,
Yeah, yeah.
I'm not trying to wind you up, but there's a sort of grown up part of it as well, in that the little branch of the government department within which I work is responsible for a couple of the major national facilities that we are involved with here in Australia. One is on home soil, or at least partly on home soil. That is the Square Kilometer Array,
Hmm.
which, as you will know, will be, when it's built, the world's biggest radio telescope, with a low frequency component in Western Australia, a really radio quiet region of the world, the mid frequency component in Southern Africa, actually in the High Karoo region of South Africa. The mid-frequency component will use dishes, very much along the lines of what we imagine a radio telescope to look like. But the low-frequency component in Western Australia will consist of 131,000 Christmas trees, because their antennas are about 2 meters tall, a little bit higher than me, and they look just like a Christmas tree. They're
Yeah.
an unusual kind of dipole. 131,000 of these, which means the telescope is steered electronically. It's not pointed by bearings and things of that sort. It all happens in the computing. So that's one component of the branch that I work in. The other is that here in Australia, since 2017, in fact, we've had a strategic partnership with the European Southern Observatory, which, as you know, run telescopes in Chile, in particular the very large telescope at Cerro Paranal, which is a misnomer because it's 4 telescopes, not 1.
Yeah.
But the VLT is a facility that Australian astronomers can now access because of this deal
Right.
done between the Australian government and ESO. And so we administer that as well.
Right. How is Australia? Because last time I was, or the last time and the only time I was in Australia, the quality of the seeing blew my mind. You know, here in Canada, we get the core of the Milky Way just barely rising above the horizon, and then for 1 month in the summertime, and then it heads back down, and then it's gone. And that's where the planets also follow this sad, dim pathway across the southern horizon. For you, they go right overhead. The core of the Milky Way goes right overhead. And the clarity of seeing the Milky Way without all of that muck of the atmosphere was like, it just blew my mind. The way I describe it, and I wasn't even in the darkest outback. I had trouble finding constellations that I knew were in front of me because there was so many stars, and they were so clear that you couldn't tell where the bright stars began and the dim stars ended. It was stunning. Why are there not more big observatories in Australia?
That's a great question, and you're absolutely right. It was the galactic center, the center of our Milky Way galaxy, that brought me to Australia in the first place, because I had to observe variable stars in that region of the sky. This is about 150 years ago, something like that.
Yeah, relativistically speaking, yeah.
Yeah, so that's right. Time dilation and
Time
all the rest
dilation,
of it.
yeah.
So the telescope that I came to use for that is the biggest telescope, optical telescope on Australian soil. It's called the Anglo-Australian Telescope. It's on a mountain, as I mentioned, Siding Spring Mountain, about line of sight. It's about 350 kilometers from Sydney. Now that mountaintop is only about 4,000 feet high. It's relatively pointy. It's not one of these long flat things, and that's because it's part of essentially the remnants of a volcano that was quite active 13 million years ago. But so that's one of the problems that we face in Australia. We don't have any really high mountains, and the other thing that we don't have is really high mountains on the western seaboard. So that telescope that I've just mentioned is actually, it's only, as I said, 300 or 400 kilometers from the east coast. And back in the 1960s and 70s, when people looked at the kind of geographical conditions that you need in order to make it worthwhile building very large telescopes, which need that exquisite atmospheric quality in order to work properly, as you said, what we call good seeing. You need a minimum amount of turbulence in the atmosphere. So the scientists in that era looked at the geography, and it turns out that the best sites in the world, and you've only to look at a map of where all the world's biggest telescopes are, they're on the western seaboard of a continent. They're at middle latitudes, which gives you actually the most nights available in a year. And they also are high, more than about 12,000 feet, 3,500 meters. Now, we don't have that in Australia. So whilst the site at Siding Spring, where the Anglo-Australian Telescope is, and I should have mentioned it's got a 3.9 meter mirror, so it's kind of comparable with the Kitt Peak telescope.
Yeah, that's a reasonable telescope.
It is. But the site that it's on, whilst it's good, and it's certainly better than anything that there is in Europe, it's by world-class standards, it is a second-class site. So it doesn't compare with Mauna Kea, for example. doesn't compare with Cerro Paranal in Chile, Mauna Kea, of course, in Hawaii, doesn't compare with Roque de los Muchachos, which is in La Palma in the Canary Islands. That's about 3,000 meters. It's got this propensity for the turbulence not to be excellent, if I can put it that way. And I'm not saying it's rubbish all the time, because it's not.
Yeah.
It's, you know,
I mean,
it's certainly
being
better
able to
than,
drive there from
yeah.
Sydney in a couple of hours is a nice advantage.
Yeah, absolutely. And that's one reason why the telescope has done so well. It's a little bit more than, it's actually about a 5-hour drive, but that's fine to the telescope. But there is a town nearby. It's an attractive town, which is a place where people enjoy living. I lived there for 25 years and I had a great time.
Yeah.
So all of those things do combine to give you in a sense, they give you a well-being for the telescope that allows you to keep it up to date. And so the Anglo-Australian telescope, for all it's now 46 years old, is still doing frontline research. And that's partly because of the kind of science that we do.
Yeah.
What we don't do, and I'm saying we because I used to be the astronomer in charge, I'm not now, but I'll still say we. What we don't do is this, high resolution imaging that we've got used to seeing from telescopes like the Keck telescopes in Hawaii, like the VLT in Chile, where they use adaptive optics systems to correct for the turbulence of the atmosphere. We can't do that at Siding Spring because there's too much turbulence there. And so we've concentrated instead on spectroscopy, the science of breaking up starlight and galaxy light into its rainbow of colors and looking at that barcode of information that's in there.
Yeah.
And we've done that in a rather unusual way too. We've used optical fibers in order to allow us to look at more than one object simultaneously.
Can you talk about that technique? Because I know you were at the forefront of that.
A long time ago, that's right. So it wasn't actually invented here in Australia. The idea came from a scientist by the name of Roger Angel, who's in Arizona. He's at the actually University of Arizona Stewart Observatory down in Tucson. And he was recognizing in the late 1970s that the communications industry was producing optical fibers which had very, very high transmission. In other words, you put light in at one end and a kilometer away at the other end, you're still getting almost the same amount of light out of it. And he recognized that had potential for astronomy. He then figured out that the best thing you could do with it is to use these fibers to sort of rearrange the objects in the field of view of a telescope. You're playing God almost. So when you've got a telescope which delivers an image, it might have thousands of stars or thousands of galaxies within that image. And you want to know the intimate details of all those objects. And the way to do that is to take a spectrum of each object. But if you're doing that one at a time, it takes you a lifetime. And that's kind of how things were when I started in this game. And so Roger Angel's idea was to use the flexibility of the fibers to pick off the light from the objects that you're interested in and then line them all up. Because that's exactly what you need for a spectrograph to make all these beautiful rainbow spectra of the target objects.
It's a stunning piece of engineering when you see these. It's like a disc, like a metal disc, with a little hole for every galaxy that's going to be in your field of view, and then a little piece of fiber optic that is poking through this field of view, and then you're able to just perfectly get that light from that one galaxy. And it blows my mind to think about just this idea, right? That you would sort of hard code the sky above in this very detailed way. And yet, we look at some of these really incredible sky surveys that have been done, some incredible work has been done with this technique. It's very successful, very productive way of observing large amounts of the night sky to get this spectrographic data.
That's exactly right. What you've described is precisely what we did in the early days, because it was the only way we could think of to do that alignment of each fiber with its target object. Because you need to make that alignment with an accuracy of round about 100th of a millimeter. So it's no good just plonking optical fibers anywhere. They're only a tenth of a millimeter in diameter anyway. So it all becomes a high precision venture. And what we did in Australia was turn it from an experiment, which is actually what Roger Angel's group did. They did develop it to quite a large extent, but I think we kind of ran with it a bit more in Australia. We took the idea of drilling holes in plates. That all worked well until we realized that it was costing a fortune to have all these brass plates with lots of holes in them. And so in conjunction actually with the University of Durham in England, we started devising robotic instruments where you could use a machine to position the fibers. And in fact, the main system, which is still in use on the Anglo-Australian telescope, was developed in the late 1990s, is an instrument with an absolutely uninspiring name of 2DF. And 2DF stands for 2-degree field. That's the field of view that the telescope sees. And the way it works is that you have a steel plate, and each optical fiber has a magnet attached to it, so it will stick to the plate, and it's got a little prism on the end so that the light from the mirror can actually get into the fiber through a right angle. And that 2DF machine had 400 of these optical fibers and a robot that then positioned each one of them in turn.
How long would that take for the robot to?
Well, it takes about an hour, but
Okay.
the clever thing is that you have two of these. So you have one that's looking at the mirror gathering light, and another one that's being set up by the robot, and then you interchange them, you switch them around.
Yeah.
So you don't lose any time. Forgive me if I finish the story off though, because my role in all this was to produce the world's first truly wide field fiber optic system, which is on an instrument called the United Kingdom Schmidt telescope, which has a field of view of 6 degrees. Big enough to take in the whole of the Hyades star cluster easily. And that we built a succession of instruments culminating in a robotic machine with the name, which is quite predictable, of 60F, the 6-degree field. But now there is a new version of this, which is still being commissioned on the telescope, which gets rid of the robot and positioning these things one at a time. Each optical fiber, and there are 300 of them, has its own micro robot built into it. So it just kind of walks across the field of view of the telescope until it's in the right place.
That's
and
so
you do them
cool.
simultaneously. Guess what they're called? Star bugs, because that's what they look like, little bugs walking around inside the telescope.
And so each little bug is sort of the end of a fiber optic cable, and it's crawling around in the field of view to position itself so that it's perfectly aligned with the galaxy that you're attempting to view, or star, or whatever you're trying to do your spectrographic field of view on. And then you take your picture, and then the little bugs reassemble themselves for whatever you're trying to look at next. That's incredible. I had no idea. What an amazing technology. That's so cool.
What's interesting to me about it is this is exactly what we envisaged back in 1982. But the technology was, nowhere to be seen. But now that microengineering technology is all there. It's mechatronics is the name of the game. Artificial intelligence plays its part. So these little fibers know where they've got to go. And there's a kind of feedback mechanism so that you know when it's really got to where it's supposed to be.
Yeah.
It works really well. Much cleverer people than me have built this thing, but I was there at the beginning.
So we talked about how Australia, although it does have beautiful skies, is mediocre for visible astronomy. And you talked a bit about radio astronomy. So let's talk a bit more about the Square Kilometer Array and sort of where we are in the state of its development and what happens next, because that's a game changer. That is as impactful an observatory as the extremely large telescope, the Vera Rubin telescope, James Webb. I mean, it is up there with the Large Hadron Collider. It is one of the most important scientific instruments that humanity will ever create.
You've hit the nail on the head, Fraser. It's big science, and that means international collaborations. And yes, people have to think things like CERN, the Large Hadron Collider, things like the GMT, the Magellan Telescope. It's a project of that magnitude. Something like $2 billion will be invested into it by up to 15 nations, in fact, many of whom have signed up already. What's delightful about this, and I'll just step back for a minute if I may, is that just under a month ago, it's about 3.5 weeks ago, we celebrated the 75th anniversary of the very first radio astronomy observation made in Australia. And it was made actually not very far from where I'm sitting, at a place called Dover Heights. It's on the east coast of Australia, and it was a World War II radar station. And a handful of astronomy-minded engineers said, maybe we could use this for something else. And in fact, they on that day, 75 years ago, they observed the sun rising over the eastern horizon and got the first radio signal for an Australian radio telescope. Fast forward 75 years, and what we're in is a situation exactly as you've described, with this mega project on our doorstep. And but that's not, it doesn't sort of exist in isolation, because Australian radio astronomy has evolved over that 75-year period. We had the Parkes radio dish built in 1961, a 65-meter dish, many other similar facilities. And Australian radio astronomers have always had their eye on the big one. So they've essentially been very clever. They've built a number of what we call precursor instruments, instruments that will test the technology. And they've also done a huge amount of work on looking for the very best site on which you can build an instrument like that. So that was the first thing to sort out. It is a place in Western Australia, very, very remote, was once a cattle station, but is now essentially devoted to the radio astronomy fraternity. It's about for anybody who knows the geography of Western Australia, about 800 kilometres northeast of Perth, which is the capital of that state. Radio quiet with, you know, to an extraordinary degree. That's to say, no mobile phones, no microwave ovens, nothing that can actually leak radio radiation. And perhaps very importantly as well, it pays tribute to the traditional owners of the country on which it's being built, the Wadjuri people of Western Australia, who are playing a part in the development of this. So the precursor instruments have been built on that site to take advantage of the radio quietness. And there are two of them. One is called ASCAP, which you might not be surprised to hear stands for Australian Square Kilometre Array Pathfinder. So ASCAP is the first Pathfinder. And in fact, it more resembles the dishes which will be built in Southern Africa, because this is a mid-frequency machine, whereas the SKA itself in Australia will be at the lower end of the frequency range. And so there is also a precursor for that, which is called the MWA, the Murchison Wide Field Array. Murchison is the name of the observatory site. So those two telescopes are doing fantastic work, even though, you know, they're a small percentage of what we will have available when the Square Kilometre Array itself gets going.
And I think, you know, when we talk about, like we saw what happened with, say, the Event Horizon telescope, where you had radio telescopes around the world working together as a giant interferometer, as one telescope the size of planet Earth. And so you're thinking, well, if you could have a telescope that's as big as 1 kilometer, how does that compare to a telescope as big as the entire Earth? So can you explain, when you say a square kilometer, what does that mean compared to an interferometer the size of planet Earth? Why is that better than all the telescopes of the world working together?
So that's a really good question. And it comes about because the square kilometre is, as it was originally envisaged, that was going to be the collecting area. 1 million square meters. So if you imagine, as it was thought to be originally, a whole set of dishes, and take the area of each dish, right, and then you add it together, a square kilometer, 1 million square meters. Now it's changed slightly because it's a lot harder to work out the collecting area of a Christmas tree, because these are antennas that just stand up from the ground. But it will still be something like a square kilometer collecting area. So that, of course, is infinitely more than the Event Horizon telescope had. That was, if I remember rightly, 8 facilities around the world. probably the biggest ones were 20 or 30 meters in diameter. So even when you add all that together, you don't get anything remotely like a square
Yeah,
kilometer.
I just
What you
did the
get,
math. The
okay, good.
the Chinese fast telescope
Yes,
is a 500-meter telescope. It gives you a area of 0.2 kilometers.
there you go.
So
That's
it's
right.
so it's it's still a fifth the size of the square kilometer array, the biggest
Yeah.
telescope that's ever been built. One single telescope. This is going to be bigger by a factor of five, at least.
Yes, that's right. And of course, the great thing about this one is you can point it anywhere, whereas fast tends to look mostly upwards.
Well, yeah, exactly.
um,
Wherever the hole in the ground happens to be pointed today.
happens to be pointing, yeah.
So
But so
yeah, we'll talk about
sorry,
that, and then I want to talk about that Christmas tree because it is a radical design from
very
I
much
think
so. Yeah.
what we envision a radio telescope to look like.
Absolutely. Just the difference between the SKA, the Square Kilometer Array, and the Event Horizon Telescope is the Event Horizon Telescope has these telescopes separated at vast distances. So you get the resolution, you get the detail, enough detail to see an event horizon at whatever it was. I can't remember how many
Yeah,
million light years M87 is away as the crow flies. Whereas with the Square Kilometer Array, you do get very high resolution, but it's the collecting area that
yeah.
is what makes the big difference. So turning to the Christmas trees, look, I'm not a radio astronomer. My background is in optical astronomy, but I do get kind of what's happening because if you think about these things looked at from above, they are cross shapes like that. The Christmas tree consists of a whole set of these dipoles, as they're called, steel bars, actually aluminium bars, placed at right angles to each other along a central axis. And Christmas tree shaped because they get smaller as they get nearer the top. And that sort of, we're familiar with that from VHF television antennas.
Hmm.
You're far too young to remember the old
Oh no, I
ones.
remember. No, I was there. I we had a giant antenna on my my dad was super like nerdy and he built a big
Okay.
VHF array on top of the house and
Okay.
we had this dial that I would turn and it would turn this big antenna on the top
Oh,
of the house
fantastic.
so
Yeah.
that I could get different TV stations. And so if one station worked well, we could get the CBC and then we would turn it and then we would get CTV. And yeah, no, I that was my
So
childhood.
you're
Yeah, yeah, I'm
crossover.
exactly that age. No problem.
But you would know then that the longer the antenna, the lower the frequency. It's all about wavelength. Low frequency equals long wavelength. So you've got a long dipole antenna that will be responsive to a low frequency. But with the SKA, you want to be sensitive to a number of frequencies. So you basically just put the dipoles one on top of another, and they get smaller as they get nearer the top, which is why it just looks like exactly like a Canadian spruce tree when its pine needles have fallen down. There's a mixed metaphor for it.
Yeah. So I want to talk about this difference because we talked about how if you are able to set up these telescopes across planet Earth, they can act as one telescope. And yeah, if you want to look at the event horizons around supermassive black holes, that's your machine. But if you want to look at anything else, you need something with that larger collecting area that's going to be able to look at fainter targets. So what kinds of fainter targets will you be able to look at with something like the Square Kilometer Array?
Yeah. So the Square Kilometer Array is very much a general purpose instrument. One of the things that we prided ourselves on with the Anglo-Australian telescope when I was astronomer-in-charge was that we had a suite of 17 different auxiliary instruments. So we were all things to all astronomers. Now, the SKA isn't quite like that. It's kind of all things to all radio astronomers. It's not quite like that, but it is certainly capable of looking at the whole history of the universe.
Mm-hmm.
Maybe the most glamorous thing that you can think of is to look back into the Dark Ages, that period after the Big Bang, before the first stars switched on, when we know that the universe was full of these veins of highly dense hydrogen, cold hydrogen, which actually emits in the radio spectrum, so we can detect it. But the key thing about the Square Kilometer Array is it is a wide field telescope. The event horizon is focusing in on one tiny bit of the sky. SKA is a survey instrument, essentially. It will look for things like pulsars, which are rotating neutron stars emitting these brief flashes of radiation. And it will do that not just for stamp collecting, it will do it because we believe that pulsars actually have the potential to test Einstein's general theory of relativity to its limits. We've got to find a place where it starts falling apart, because that's where new physics is. We haven't found it yet. So that's the kind of thing, as well as perhaps, one of the ambitious things I think is going to be very, very exciting is going back to those dark ages. Of course, the further out into space you look, the further back in time you're looking. So you're looking back 12 and a half, maybe 13 billion years to when these strands of hydrogen were basically the building blocks of the universe. And not only to detect them, but to actually map them across the sky.
So how will the Square Kilometer Array, and apologies for my Canadian accent. You're saying kilometer and I'm saying kilometer.
Look, everybody says kilometer here as well.
No,
I'm just pedantic.
No. We're as Canadians. A lot of people make fun of me for my Canadian accent, like the way I say lava and the way I say resources and things like that. But the one that I will admit that we say it wrong is kilometer. That we should say kilometer. It's kilogram, kiloliter. Exactly. It should be kilometer, and yet we say kilometer. It's something wrong with our country, and I just want to apologize. Kilonova. Yeah. But anyway, so again, I will always say kilometer because it's just in my head. But you're looking back to the beginning of the universe. You're seeing this hydrogen, this primordial hydrogen that is left over from the Big Bang. And what are you detecting with the array?
So actually you're directly detecting it. This needs exquisite sensitivity on the part of the telescope, and that's why it's a square kilometer. But what you're detecting is the hydrogen itself. You're looking at it's this transition between the state of the atoms of hydrogen that actually emits radiation with a frequency of 1427 megahertz, which is a wavelength of 21 centimeters.
Yeah. Centimeters is the one that everyone's is familiar with.
Everybody thinks of. Yeah, I'm just showing off here.
Yeah. No, you translate it into meters. That's beautiful. Yeah.
It's because I'm a neophyte radio astronomer. I've never thought of megahertz in my life before until I've become mixed up with the SKA. So 1487 megahertz, and so that's the frequency with which that radiation is emitted.
Yeah,
and it allows you. We've been doing this ever since the dawn of radio astronomy, but doing it in our own backyard, if I can put it that way.
Yeah.
Mapping the spiral arms of the galaxy was one of the early triumphs of radio astronomy, because you could see this hydrogen throughout the spiral arms of our galaxy. Now we're looking for these strands of hydrogen 12, 13 billion light years away in the early history of the universe.
It's such an important thing to think about, as you said, that this technique of mapping the 21 centimeter line, that you have this enormous cloud of hydrogen, then every now and then hydrogen, one little hydrogen atom in the blob will release this photon, but it's always this exact same wavelength. And so wherever you look and you see those photons coming at you, there is hydrogen there. There is raw material for forming stars, and we see it in the galaxy. But the galaxy, we're already pretty familiar with all the processes. We can look at it with all these other wavelengths at the stars, and we can see the stars and the clouds of gas and dust and so on. But when you look out to that first period, right at the very beginning of the universe, really right after, that's the mystery. The Dark Ages is such an evocative term, because now you're looking back, and again, this idea of thinking backwards in time, you're seeing the entire universe's store of hydrogen before it turned into the galaxies that we see today, where was it? How was it distributed? How was it coming together, flowing like water into larger and larger formations? There's so much that we don't know about the universe today that we can't know until this telescope comes online and
Yeah.
tells us this answer, because no other machine can peer into that period yet.
That's right. And the other thing, of course, that it tells us is the hydrogen, we believe, concentrated in regions of a high density of dark matter. And we don't know what dark matter is yet,
Yeah.
but we know it was there. And we believe that it played a crucial role in setting up this framework, the scaffolding of matter within the universe, which eventually became the galaxies and the clusters of galaxies
Yeah.
that we see today. So one of the things that we'll be able to do is something similar to what we do with the cosmic background radiation. When you, which is that radiation that covers the whole sky, it's the flash of the Big Bang as we're seeing it, as it 13.8 billion years after the event. That has regions of slightly warmer and slightly cooler temperature. And by analyzing that, you can actually learn a lot about the conditions within that fireball, which formed the Big Bang. So you're able to do something similar. If you can build a map of the structure of these hydrogen clouds or strands or framework or whatever it is, then you can do the same kind of analysis on that. And that gives you an intermediate stage between the universe at the Big Bang and the universe today, which tells us something about the evolution of the universe and may illuminate one of the other big problems that we don't know about, which is dark energy, this stuff that makes the expanding universe accelerate in its expansion. So it sort of feeds into all that stuff too.
Yeah, it's interesting. I mean, like we're very familiar with, say, the Hubble Deep Field and the Hubble Ultra Deep Field, and I'm sure, and that's you going from now to try to look back in time, but you're limited to about 5 billion years, and occasionally you can see a little farther. And when you take something like, say, or I guess closer to what, 12 billion years? I forget the exact distance that the deep field. But you take, say, James Webb, it's going to do its version of the deep field and go even farther, closer to the beginning. But still, you have this dark age. And so when the square kilometer array comes online, I'm envisioning this version of the deep field, but it is purely primordial hydrogen in all directions. We will have this picture of the primordial universe before there were stars, before there were galaxies. It'll be one of the most important surveys, one of the most important pictures, I think, that humanity has ever created. And we are still a decade away from getting our hands on this picture. I mean,
hopefully
again,
not quite a decade, but getting on for
well,
that.
when's first light for square kilometer
so
array?
it's in the region of 2027, 8, 9, perhaps.
Yeah.
Towards the end of the decade.
Yeah.
And just to actually answer a question that you asked 20 minutes ago,
Sure,
yeah. The status at the moment is that the observatory itself, the Square Kilometer Observatory, as a sort of formal entity, will, we hope, come into being before the end of this year.
Yeah.
And that will allow, that puts in place the mechanism whereby contracts can be let for the structure and the electronics and all the rest of it. And that process, we hope, will result in construction of the telescope starting certainly in Western Australia in the second half of next year.
Yeah. I mean, I guess one of the great things about this is you can kind of grow the telescope organically and gain more functionality as you go. And, I think we'd be remiss to not talk about the fact that the similar process is happening in Australia, in South Africa, with a similar scale, incredibly technical telescope there with Meerkat and moving on with that, right?
Yes, absolutely. So the other half of the SKA is in South Africa. It's actually an evolution from the Meerkat facility. I love the name Meerkat. It beats ASCAP into the ground.
Yeah.
And do you know how it was derived? It's a
it's a
really
backronym, obviously, right?
It's a kind of quasi acronym. So the original plan, and this is a precursor for the Square Kilometer Array in South Africa. The original plan was to build something called the Karoo Array Telescope. The Karoo is the region of South Africa. Karoo Array Telescope, that's the cat. So they said, we're going to build the cat, and that everybody was happy with that. And then the South African government increased the funding so that they could build, I think, 60 antennas rather than 30. So that they decided to call that Moorcat, which in Afrikaans is meerkat, which of course is one of these,
Yeah, well, those little critters.
lovely,
Yeah, that's beautiful.
lovely work there with the name.
And I want to get on to talking about Starlink, but I just wanted to add one more thing that makes me really excited about the Square Kilometer Array, and that's for the people who are, really excited about the search for extraterrestrials.
Yes.
It will be the most powerful tool again for detecting. And the quote that I always like to run with is that the Square Kilometer Array will be capable of detecting Earth's radio traffic, like just for airports, airport radio traffic, for about 100 light years.
Yeah, that's right.
Not even directed. Like, it's just like, if we had, when the Square Kilometer Array is rolling, we can just point it at various stars and go, oh, they've got airlines there 100 light years away.
They've got airport radar.
Yeah,
That's right.
and they're not even intending to transmit in our direction. So, all right. So let's talk a bit about Starlink, because Corey S asked in the questions, are you seeing the effects of Starlink, and how's it affecting observations? We've heard a resounding thumbs down from the visible radio community. It's way worse for radio, isn't it?
It is. That's right. And I mean, look, it's bad news for, as you say, for the optical community, and in fact, the amateur astronomy community, I think, are the ones who will be most affected by this, because they tend to use, particularly for dark sky imaging, wide field telescopes, long exposures, and you've got the risk of these spacecraft going through your field of view.
Yeah.
Among the professional optical telescopes, the one that will be most affected is the Vera Rubin telescope, because it's the same thing. It's a wide angle telescope, this time with an 8.4 meter mirror as well. So it's very, very sensitive. Now, SpaceX have certainly been attempting to respond to this problem, and they've got what they call, I think it's VisSat, is that right, or VisorSat? These are essentially visors.
VisorSat, yeah.
And they, I think the last several hundred of the Starlink spacecraft have been launched with those, which should, at least to some extent, mitigate the problem for optical astronomers. But as you said, Fraser, it is vastly more difficult for radio astronomers. And in particular, when we look at the higher frequencies. So the Square Kilometer Array in Australia will be affected, but far less than the Square Kilometer Array in South Africa, which looks at frequencies, if I remember rightly, up to about 15 gigahertz. Throwing around these numbers again. Yeah. Those frequencies include some of the really interesting frequencies when you're looking at organic molecules in dust clouds and things of that sort, which we might find, these are the places which might harbor life to be discovered later on. So one particular band of the transmission of Starlink coincides with one particularly important band in the retinue of radio astronomers. It's actually right next to it. So the worry is that you'll get leakage across into the radio astronomy band. So there are talks underway as we speak about the possible mitigation strategies. For example, as the Starlink spacecraft are flying over the High Karoo in southern Africa, whether their antennas can be deflected so that they're not beaming directly down at the antennas.
Yeah,
the
problem. I was just going to say. So with the visible telescopes, like the Starlinks are bad, say in Canada during the summertime, because you get them visible for the entire field of view. They're bad in the southern hemisphere, again in the southern, in the in the winter months for the northern hemisphere. In the southern hemisphere, it's their summer. Same thing. You get a longer transit across your sky. But radio astronomers work in the daytime. So there's no time when these aren't going to be going, they're not visible because they're heading straight over the way it is with visible telescopes. They're just going to be screaming as they go overhead. But is that like, but the fact that they can turn off that radio transmitter as they pass over a really important radio telescope, that seems like there is a ray of hope that you don't get from the visible side.
That's right. And as I said, discussions are in place or in progress about that. The Square Kilometer Array organization released a fairly lengthy document about a month ago, which elaborates on exactly what the effect is likely to be on the Square Kilometer Array in South Africa, and suggesting the remedial strategies that Starlink that SpaceX might like to put in place. And I think those discussions are ongoing. I'm actually in a meeting the day after tomorrow, Fraser, which is concerned with exactly this issue. So if we've been talking a couple of days hence, I might have been able to tell you a bit more than I can.
Yeah. Well, let me know if you convince them, because I think this is definitely within their power, I think, for them to just turn off the transmitters when they're flying over important radio observatories. As soon as they're over the horizon, turn the transmitter back on and everybody gets their internet. But let's try to maintain the science in a way. I mean, it's just not done. Like airplanes fly around observatories because of this, they don't want to mess up the photography. So I think this, obviously you can't change the trajectory of your satellite in the field of a visible telescope, but with these radio telescopes, you can mitigate this.
Except there is a gotcha there, and that is the way that Starlink, for example, and of course we're talking about OneWeb as well. That's another of these.
And whatever the Chinese launch, whatever the Russians launch, there's no going back. Yeah,
there's many of them. So for the Australian Square Kilometer Array, there might be a problem that is actually less tractable, and that is, even though the Australian telescopes have low frequencies which are not sensitive to they're not the same frequencies that the Starlink spacecraft are broadcasting on. What they do, if you've got all these spacecraft above your horizon, you get a reflection from terrestrial radio signals. So somebody in Perth,
right,
in radio radiation, it's picked up by a spacecraft over the Murchison Radio Astronomy Observatory, and you get a reflection back down to the ground.
Yeah, that sounds like the WOW signal.
That sort of thing. That's right. Whatever the WOW signal was.
Yeah. Possibly a reflection.
Yeah, possibly a reflection. That's right. And that is it's a lot harder to see how you can mitigate that, because what you've got to then do is say, okay, everybody within 500 kilometers radius or 500 miles, whatever, turn your emissions off, and that's never going to happen.
Right.
So it's one of the problem. One of the things that surprised me when I talked to radio astronomers who are involved with the Square Kilometer Array, they are worried about the reflection of terrestrial radio transmissions off the moon. So stuff that's being broadcast on the moonward side of the Earth, going to the moon, coming back and messing up the observations in the SKA.
So the moon is a pain even for radio astronomers.
Look, I won't hear a bad word against the moon. It's my favorite celestial object.
Really? I would push it into the sun. So
yeah. So, well, maybe it's it might be already over, because it's probably because of the moon that we're here and we're talking like this.
Fine, thanks, moon. Yeah, there. Does that settle it? Does that even the field? And now I can push it into the sun and just get rid of it, so that we can have more nights of observing. Because, only being able to use a telescope half the month is sort of, it's just not fair.
But look, you don't have to worry. In about 50 billion years, it'll be so far away that it doesn't actually matter anymore.
Nor will there be a sun for it to reflect the light off of. So, that problem will sort itself out. All right, let's get some more questions from people. We've got just about 5 more minutes. let's see. So JWW asked, what is your biggest discovery that you were a part of? What is the, what is where do you get your Nobel Prize from? What will it be for?
Yeah, I have to say I'm still waiting for that,
Yeah.
and I suspect I'll be waiting for many, many decades. Look, so the work have done as a working astronomer, certainly back in in my early era as a youngster, finding my way in astronomy, I did discover a variable star that had some interesting properties, but that was never going to win anybody a Nobel Prize. But there's one paper, a scientific paper, which is very, very highly cited, which my name is on. And that is a paper, it's about the Hubble constant. And it was a spin off from something called the 60F Galaxy Survey. So back in the early 2000s, I was project scientist for a survey. Actually, I beg your pardon, I was project manager, should get that right, for a survey of about 150,000 galaxies using this fiber optic technique that we were talking about. And so we mapped them across the entire southern sky. One of the things you can do with a wide field telescope like the UK Schmidt telescope is to do that entire sky, not just little sight lines through interesting bits of the galaxy. So we did the whole sky. Apart from the Milky Way, we're looking at galaxies the Milky Way blocks their light off. And from that, we determined lots of things about the structure, the large-scale structure in the vicinity of our own galaxy. These galaxies were only out to about 500 million light years, 500 million light years, not very far. But one of the things that it allowed you to do very cleverly was an independent, if I can put it that way, determination of the Hubble constant within about 2%, something of that sort, completely independent of Cepheid variables or any of the other normal techniques that are used. Now, I have read that paper many times. I'm not convinced that I still fully understand it because I wasn't the first author, but I was responsible for all the data,
Yeah.
and it means that my name goes on it, and I'm very honored to be part of it.
Well, and now with the ongoing crisis in cosmology, it's even more important for people to have
Yes.
various independent methods of measuring the Hubble constant. So I wouldn't be surprised if people are digging into that paper and going, can we replicate the result and can we try to bring down those error bars? So I wouldn't be surprised if you see your name pop up, more and more as time goes on. Well, we've
Yeah.
reached the end of our hour. I don't want to take any more of your time, although I know it's your day has just begun tomorrow for you. But if people want to follow what you're doing, where should they go? How can they sort of keep track of your busy activity?
So I have a Twitter feed, which I'm probably not as active as I should be. It is at StargazerFred. That's I try and, if I'm doing anything really interesting, I try and mention it. Sometimes it's boring stuff as well, though. Never mind. But perhaps the best way, and I don't want to in any way steal your audience, Fraser,
I
but
I
we,
beg you to steal this audience. They would love to come I think, for those of you who are not in Australia who have, I hope they've all become fans of this conversation, and they will stampede to come
that would be great.
and check out everything you do. So where should they go? What should they do?
They should go to the Space Nuts podcast, which you can
Yes,
find pretty well everywhere. Space Nuts, every week we do a podcast. It's a gentleman by the name of Andrew Dunkley. I talked to
of
him.
course.
He was a radio presenter. He and I spoke together for many, many years, and then he retired. He did the sensible thing that I hope I will never do. He retired, but we decided to keep the podcast going. Keep the talks going as a podcast, and we've been at it for 3 or 4 years now, and
Wonderful.
seems to be very popular. It's a lot like the conversation you and I have had, actually, Fraser, because it tends to go off in all kinds of weird and wonderful directions, and includes stars like there's a rooster that hangs around here, and he occasionally contributes little gems of knowledge to the discussion. So
Okay.
Space Nut.
Space Nuts podcast, and we'll put a link in the show notes so people can check that out. Well, Fred, always a pleasure to talk to you, and I cannot wait. Again, you can tell how excited I am about all of the really interesting stuff that's happening. We didn't even talk about your new space administration. That'll have to be a conversation for a future discussion, because that's all coming together as well. So everything is just sounds really exciting in Australia, and definitely come back in the future and let us know what's happening.
I'd love to. Thank
All
you very
right.
much, Fred. It's a
All right.
great pleasure to meet
Take
you.
care. We'll see you again. Thanks, everybody. Oh, and everybody, before I just hang up, remember, if you've got a bunch of questions that we didn't get to in the chat, go ahead, put them in the comments. I will gather a bunch of them up, and I will answer them in some future question show. I look at them all. I see everything. I'm everywhere. I'm in your mind. Thanks. We'll see you next week.